Okay, we're back. Yeah, so that was a review, and I did it mostly because most of you are not here, and also because it's important, and also because, whatever, it doesn't hurt to have a bit of a review. But it's time to get on to new things. And this is where we have case 2. So, case 2 is what we call second class, or what Dirac called second class constraints. And this is when the constraints, let's call them phi little I, still Poisson commute with Hamiltonians. But they no longer Poisson commute with each other. And so you get J Fij. And these can be, in principle, they can be arbitrary functions of the Q's and P's. Of course, this has to be an antisymmetric function, of course, of Ij. Antisymmetric, not function matrix. So, good. Now we're kind of screwed because we can't do the same thing that we did before. We can't just use Darbo's theorem to go to coordinates that on the constrained surface are going to all be orthogonal, because these guys are messing that up. Okay, so we can't use Darbo's theorem anymore. But if we're lucky enough, we might still be able to find a way to correct the Poisson structure in order to get something that's still valid. And so there's two cases. One case is if these functions, Fij, are invertible, and invertible on the space, on the, they're kind of matrix space. So if they're invertible functions, and I'll kind of be more clear what I mean by that in a second. If they're not invertible, then you're screwed. Then you typically just have an inconsistency. So the Euler-Lagrange equations are a necessary condition to have a stationary point in the action, but they're not a sufficient condition. So you can just have situations where there exist no solutions. There are no stationary points. And this is, if you run into a situation where you get this kind of thing, your constraints are just not consistent with each other. They'll just keep wanting to send you off the constrained surface, and you just can't. You can't stay on the constrained surface, so your theory is inconsistent, or there's just no solutions. Okay, that's a possibility. The second possibility is if this is invertible. And then what you can do is you can you can use a new bracket, which basically projects the symplectic structure onto this thing, and then you can kind of fix the symplectic structure in a way that is more canonical. So I'll show you what I mean precisely in a second. So what does this mean? And what do I mean by invertible? What I mean is that what we want is we want these things to commute on the constrained surface. So if I define some Lagrange multipliers, lambda I phi I, phi j, then I'll get an equation that looks like lambda I Fij equals 0. So, in some sense, I'm looking for a set of Lagrange multipliers that I can use to make this 0. And I can do that if f is invertible on this space. And if I can't do that, then I'm in this situation, right? So if f inverse exists, and in particular, what I mean is, I have a function, ij, that when I contract with this, just gives delta.
Why can you not do this when f is not invertible?
Because then, well, if f is not invertible, then there are no, you're looking for the null space of this thing. And so if it's not invertible, then it doesn't have a null space. So you're kind of screwed. I mean, there could be a subspace which is invertible and a subspace which isn't. Then you can gauge fix that subspace, but not the rest. So, just as an example, we did the canonical gauge fixing. So if we consider the canonical gauge fixings, then we just have, well, with the canonical gauge fixings, we find that these functions f are just delta functions. Keep in mind that there's a kind of mismatch in notation somewhat here. Here, these indices are ranging from 1 to all of they're ranging over all of the second class constraints. And here, my indices are only ranging over half of them, right? They're only going from the momentum and then this. So really, if I wanted the indices to range the whole thing, I would have to write a kind of block diagonal thing, which is anti-symmetric, and then it would have a 1 here and a -1 here. But anyway, just keep that in mind, that I switch back and forth between these notations. But in any case, if you use this notation, which is the most compact one, then you can see that what are the Lagrange multiplied? This is obviously invertible, and so I get an equation. If I smear this with some Lagrange multipliers, and I sum over I, then this is just telling me that lambda I equals 0, which is the canonical gauge fixing that I defined before. So there's an equivalence between trying to solve this Poisson structure versus doing it this way. So now we're just looking for a procedure that will generalize this. And it was, again, a suggestion by Dirac. So, so if you want to read more about this, you should take a look at his book, where he's a lot more formal. He doesn't have this geometric picture in his head when he's explaining, but all the structure is here. So I think once you watch the lectures, you should be able to go and read Dirac, and especially once you've done some examples, you'll be able to read Dirac and say, oh, now I get what he's saying. Now I get what he's saying. But it's kind of, I think it was you, David, who pointed out that the first time you read Dirac, it was like, what are you talking about? Yeah. But he was a clever guy, and he came up with this procedure for kind of adjusting the Dirac bracket and getting flow, which is effectively orthogonal on an arbitrary gauge fixed surface. It's actually pretty simple, right? So you define this Dirac bracket, and it just projects out the bad part of the flow that you don't want. It projects out the flow on the bad variables and just preserves the flow, part of the symplectic flow, on the reduced variables. How does it do that? Very simple. You define it this way. So the Dirac bracket on some arbitrary phase-space functions is equal to the Poisson bracket, which is the bad thing, minus, well, it has a bad piece. The bad piece is this piece, the piece you want to get rid of. So then you just take this and you literally subtract off the bad piece. Okay, so you just write minus f Poisson bracket with phi I, and then you put f inverse here, ij, then you put phi j, and then you put g. And this thing will do exactly what we want. Now remember, this is actually two pieces because you have to antisymmetrize. Okay, this is antisymmetric. I mean, it's implicit in the definition of f that this is antisymmetric, but this is actually two pieces. So I'm kind of using a compact notation here that's illustrating the point. You basically have to swap f and g in here. Okay, so how does it work? How can you see that this is going to do what we want? Well, let's just look at the flow of this on our constraints, on our second-class constraints. So what happens when we use the Dirac bracket smeared with some arbitrary phase space function? Okay, what we find is that we get the Poisson bracket. Okay. Minus, all right, now we just do the formula. Phi I with, I should have put a k index. K I, and you can almost see exactly what is going to happen here, right? Okay. So when I evaluate this thing in the first term, or when I evaluate it in the second term, you're going to get this thing, which is just fki, right? So you're either going to get an fki here, in the second term you're going to get an fki here. In both cases, it's going to contract to a delta. So this part is equal to minus, and then if you do the antisymmetrization properly, you put a factor of 2. So you get 2 times half of this piece, which is I delta k j. Delta kj contracted with kj is just Poisson bracket of phi j, phi I, and f. And you can see this cancels this. So it's set up precisely to give 0. And not just 0 on the constraint surface, 0 period, right? We've completely projected out the flow of f. We've completely projected out the flow in these directions, okay, on the reduced base space. And it's a strong equation. So then Dirac says, oh great, we can just, if we use this Dirac bracket, then we may as well just set phi k equal to 0 strongly. And then we can just stick phi k equals 0 everywhere in our system, and we know that if we use this particular bracket, that's totally fine. It's not going to change our equations of motion. Right? Perfect. So you just replace Poisson brackets with Dirac brackets. Right? And then you write down your Hamilton's equations with Poisson bracket D instead of Poisson bracket, no Poisson bracket, and you're good. So, now, again, I'm going back to this example of the canonical gauge fixings because it's good to know that they exist, and it's also good to know their properties. So whenever you can find these canonical gauge fixings explicitly, it's really useful to use them because it will really drastically simplify your theory. So, so again, with this canonical thing, what's the Dirac bracket, right? So my gauge fixing was, my constraints were this. And if I think about how the Dirac bracket acts on reduced phase space functions. So if I can explicitly find a canonical transformation that isolates pi and phi and everything else, right, then I know that those guys are orthogonal to these guys. So if I can do a canonical transformation that allows me to write these only in terms of the reduced guys, so these are functions of only qi reduced and pi reduced. Then, how does the Dirac bracket act on this? Well, it's the Poisson bracket of f and g, sorry, minus f phi I, f inverse ij, g. But if these guys only act on the reduced phase space, then these guys are just zero. And so the Poisson bracket reduces to the Dirac bracket. This is a useful case to keep in mind. So what we'll see when we do various examples is that every now and then we'll find situations where the variables that we have are just, the constraints that we have are just canonical variables. And in that case, there's a very simple symplectic reduction which you can do that has a trivial Dirac bracket. So you can basically just apply these constraints strongly, get rid of them, and then you don't even have to change the symplectic structure. So that's a really convenient tool. And we'll see that it will come up again and again in all the examples that we do. So the primary constraints for a lot of the gauge theories that we look at are like this. Okay. So again, it's still a lot of formalism, but in a second we're almost finished. Okay. Then we're going to get to some examples, and we're going to be able to kind of see all of this stuff in action. Okay. And I think that's how you're really going to learn this stuff, is by doing examples, and then go back and look at your notes, and you'd be like, that all makes sense. So the last case is case 3. And case 3 is when now the constraints, let's call them, let me just call them this. I'm starting to run out of notations, but imagine that these are not the same constraints that we're looking at in case 1 and case 2. Okay? Where these constraints are not Poisson commuting with the Hamiltonian. So they're giving you some prime, some new phase space functions. Okay? Now, in this case, there's 2 possibilities. Again, like last time, if phi prime I are just constants, then you're screwed, okay? Because you have something that you want to be 0, and it's a number. So you have something like constant equals 0, which is inconsistent. So if you run into this situation, then you're done. Your theory's bad. Okay? And that can happen. There's examples where this happens. You can see them in Hanot and Dubois, and you can see it in the book by Kurt Sotomayor. And I think even Dirac does an example. So there's just some situations where there are no solutions to the equations of motion. You can find that by doing this. The second situation, actually there's 3. But let me just focus on, let me just call them 2. So if they're not constant, okay, if they're phase space functions, then you promote them to constraints, to new constraints. So you just say, I'm going to try to restrict my dynamics to a subset of phase space which also satisfies these new constraints. And so these are higher order constraints. So Dirac called these ones primary. These are the ones that you get just by reading off the Hamiltonian. And then they can generate secondary, tertiary, but I'll just call them higher order constraints. And Dirac's procedure, okay, so his proposal is to take, so again, this is Dirac. Not everyone agrees with this, but I think it works pretty well. Is to take the Hamiltonian and just add constraints to it.
Only the primary or all of them?
Well, at this level,
you added exclusively only the primary constraints and never the secondary ones.
I don't know. Well, no, but you can. Well, I don't know. That's I don't know. Different people say different things. I never really understood the people who said that you only put the primary. I think.
Usually, you've got all of them.
The point is that you can look at the same theory.
Yeah.
And in some cases, a certain constraint arises as a primary, and in other cases it arises as a secondary. But it's actually the same theory. So as far as I can tell, the primary, secondary, tertiary distinction only matters on how you found the constraints in the first place. And so
it's completely irrelevant.
Yeah.
I
disagree. You're getting this from Pons and Salisbury, I think.
No, even from my own little point, I'm still unclear of which constraints they should add. And I think Sotomayor at some point comments on the fact that it's actually equivalent to just add a primary or all of them.
Yeah. To be perfectly honest, I know that people say different things, but I can't see any problem with just thinking of this as adding, the point is that you want the constraints to be satisfied. And the easiest way to do that is to put them in your action principle. But anyway, whether you call... Okay, maybe you don't want to add them to the Hamiltonian. I can't see how it can possibly make any difference. But in any case, you want these constraints to be satisfied, right? So the Dirac algorithm is now the following. So now I have enough, I've built up enough formalism to give you the Dirac algorithm for picking apart this Hessian. So you have this Hessian, which doesn't have the right rank. This algorithm is designed to identify what the rank of that thing is, and then classify all of the symmetries and the underdetermination that exist within that the breakdown of the Hessian. Okay. So the first thing is you have to identify through whatever means primary constraints, and this is. So you have to get constraints which seed the algorithm. And I call these guys phi with a little thing 1 because they're the primary. Okay? And so Dirac doesn't actually specify a procedure for how to do this. And this is where I think there's some disagreement in the literature about there's something fundamental. But Dirac says this in his book, and I agree with him. There is no real fundamental distinction between primary and secondary, as far as I can tell. So somehow you have to find some constraints to seed this. And then you run the procedure. Then you check. Then the second step is the step where you start to collect primary, secondary, tertiary, whatever, nth order constraints to see if you can get all of them, until you get all of them. So the claim is that, the first step is you have this if Poisson bracket of the nth order constraint. Okay, so you start by saying n equals 1, right? This is the algorithm. This is literally how you plug it into a computer. N equals 1. If phi n I Poisson commutes with h, then the total number n equals n, and go to step 3. You're done. Okay? If these guys plus commute with h, you've identified all the constraints. And then you can go to step 3 and then work out more structure of these constraints. Okay, that's the first thing, because you still haven't found the rank. Okay, this n is not going to necessarily be the rank of that or the difference between the rank of the Hessian and the dimension. But else, you add new constraints, so you define phi n plus 1 I equals the Poisson bracket of phi n I with h. Okay, so you identify these as new constraints, higher order constraints. Then you say n equals n plus 1, and then you loop. So you go back here. And then you just collect all the constraints this way until you stop, until you exit this step. Now, the point is that you could get caught in an infinite loop here. So that would be case 3, is that n goes to infinity. So case 3 here is n goes to infinity. And then you're also screwed. You have an overdetermined system. There's just too many constraints, and then the thing doesn't make any sense. Once you have a set of constraints which Poisson commute with the Hamiltonian, then you have to check if they Poisson commute with each other. And this is where the first class, second class distinction comes in. So you collect all of the constraints, all of the, I don't know, there's probably a mathematical way of writing this, like the product of, or the sum of all the constraints from little n equals 1 to big N, something like that. Anyway, I'm just writing like this. You collect all of them, and you call these the constraints. Okay. And then you compute Poisson brackets amongst these guys. And once you do that, then you can classify these as first or second class. Maybe I'll call this alpha or something. I'm running out of indices. As first.
Should be Vita show.
Huh?
It's better you have a Vita.
What is it?
Alpha Vita.
Oh yeah, sure. Yeah. Thank you. Okay. Once you've identified them as first and second class. Yeah.
How do you do this? Because essentially first class is a constraint is not first class on its own, it depends on the other constraints, and the first class constraint only needed to commute with all other first class constraints, not the second class constraints.
Yes. So
That's make him second class.
that would make them second class. Yeah. Sorry. No, this is sufficient, right?
The constraint needs to correspond with.
It needs to commute. So the first class constraints need to commute with second class constraints.
Oh, okay.
Right. Otherwise, they're not first class. Yeah. 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 So you have to classify them. So you have this big matrix of constraints. You identify them as first and second class, and then you can treat them in the way that we said. So actually, I already discussed the rest of the Dirac algorithm, which is how you treat, because what you do with the constraints depends on whether they're first or second class. right? So if you have basically more options if they're first class than if they're second class. If they're second class, you basically are stuck. You have to use something like the Dirac bracket to evolve them, or you're lucky enough that they're canonical, and then you can just eliminate them directly from the theory without using the Dirac bracket. So if they're second class, you're basically stuck. You don't have too many options. If they're first class, then you have more options. But those options are basically just work with them as long as you can, and then eventually you turn them into second class constraints. Because the point is that a gauge fixing is just turning a first class constraint into a second class constraint. So you add arbitrary constraints to the theory to make the first class constraint second class, and that gauge fixes. So really, we only ever deal with fully second class systems. We can only evolve the equations of motion when we have second class constraints. But it's convenient to work with the first class constraints as long as we can. Basically because when we add the gauge fixings, then we've fixed some structure, or this becomes more complicated because the Dirac bracket can be, in general, quite complicated. And so it's better not to work directly with the Dirac bracket, but to work with the Poisson brackets and the first class constraints. So that's just a conceptual summary of what I'm going to do, but let me write this out in detail. The other thing I'm going to do, because it's so important, I didn't have time to do it last night, but I will do it probably today, is give you a handout with the Dirac algorithm in full gory detail, so that when you work through exercises or when you treat a problem, you can always just refer to the algorithm in case you forget, or I guess it's not that complicated, but the first couple steps are pretty easy, right? It's the step number 4 that's it's step number 4, which is actually important to remember. And I think step number 4 is the key thing, because once you've classified your constraints as first or second class, then you need to know what to do with them. So 4a is, so I'm calling the first class constraints little phi, capital I, and the second class constraints var phi, small I, okay? So for, I kind of said this already, but for the i's, you use, okay, so there's more than one option in principle, okay? You can, just the simplest thing is just to use the Dirac bracket. And then this allows you to say phi I is 0 strongly. Okay, and this you can use in the classical theory. No problem. It is a little awkward. We'll do an example where we have a second class system and we explicitly compute the Dirac bracket, and it looks kind of nice. But in general, this procedure is pretty awful. Okay, these Dirac brackets are not so nice, and then you kind of, well, you can do it, and that's basically what you have to do. But it's not nice. In the path integral, so at the quantum mechanical level, in the path integral, there's a kind of analog with the Dirac bracket, and that's the basically the Fedaya-Popov thing. So effectively, what you do is you do a non-canonical transformation that is equivalent to, does the same thing as the Dirac bracket. But that non-canonical transformation generates extra terms, right? A non-canonical transformation will transform the Hamiltonian. Those terms are the ghost terms, okay? So the corrections that you add to the Dirac bracket can be mimicked by adding new terms in the Lagrangian, and these are the ghost terms. So if you've ever heard of this or done some quantum field theory, You'll see. We'll get into this at the end of the course. But that's the origin of ghosts. There is another option. So if you're, I mean, of course, if you have a canonical gauge fixing, then you can just remove, then the Dirac bracket, the Dirac bracket reduces to the Poisson bracket, and then you can just remove constraints completely from the theory, not even worry about them. So that's called solving. When people say, I've solved the constraints, this is effectively one way of doing it. Okay, so you find a canonical gauge fixing. So you identify the thing that's exactly canonically conjugate to the constraint, and then you just do a reduction because you just put the constraint strongly. So here you can just say phi I is strongly equal to 0. That's what I mean by solving the constraint. There's a second option which I don't want to talk. I don't think we're going to do this in the course, but I just wanted to tell you because it's interesting to know that you can do this. It's something called gauge unfixing. So the idea is to think of this second class system. Remember, these constraints come in pairs. If it's second class, it has to be second class with respect to something else. These guys always come in pairs. And the first class constraints are like second class constraints that need to be gauge fixed. A first class constraint is like a constraint that just wants to be gauge fixed. It hasn't been gauge fixed yet. But what you can do is you can think of this pair and imagine that it's a first class constraint which has been gauge fixed. So you can effectively, if you can find a first class submanifold or a first class representation of these, like a maximal first class subspace. So they're not first class with respect to the other subspace, but they're first class with respect to each other. Then you can throw away the other part and keep the one that you have. So you kind of, I mean, the idea is you find subspace and throw away the complement. And that's kind of cool. So you just look, you scan your space here, you take linear combinations of them, until you find a subspace which is first class within themselves. But then they will still be second class with respect to the other guys. So you basically partition your subspace into a first class one and another first class one. But these guys are second class with respect to each other. And so then you just throw away either this one or this one, and then you have a new theory which is now first class. And it's cool because in shape dynamics, I can't help but say this, but in shape dynamics, you have a choice, right? If you throw away this one or if you throw away this one. And they're just different representations of the same theory. So in shape dynamics, you do symmetry, what we call symmetry trading, which as far as I know is not anything anyone's ever done before, where you just pick this one, and instead of picking this one, you pick this part. And then that gives you a totally different gauge symmetry, but it's complementary in some sense to the first one. Anyway, that was an aside. And this is mostly just an aside, but I think it's cute that you can do this. Right? And I've seen people actually do this before in papers. Okay. So this is the benefit of teaching a master's level course, as you can tell these little kind of fun facts. People won't scream at you for giving too much information. But I'm not gonna do any examples of that one. The rest of them we'll do examples of. Okay. Now case B, basically those are the only options that you have if you're I said that there is a way, like I said, there is a way to do this non-canonical transformation, which is related to this thing is, if you do a non-canonical transformation, it's related to these BRST formalism. So there is a third option, which is what people use when they quantize the standard model. But I'm not going to have time to get into much of this. Okay, probably by the end when we do the quantum theory, we'll do a little bit. But it's related to the Dirac bracket, but that's all I'm going to say about BRST. Okay, except for when we come back to it at the end. How much time do I have? How is it?
No, it's 3:37.
37? Okay. So, can I... You guys are itching to leave? Can you give me like... Oh, there's too many things. Okay. Well,
Just give us a preview of the next lecture.
well, yeah, okay. So, no, but let me finish this. You guys have to leave, or...
Yeah.
You do? Okay. 5 minutes? No, you have to leave.
Well, the last 5 minutes were the 5 minutes.
We're hard. 5 minutes.
It's being filmed anyway.
Yeah, it's being filmed. So no problem.
Check the last 5 minutes of
I would have to, even if I do now, I have to review it next time. So the part B is when you have the first class constraints, and then you have a lot more options. And so basically next week, I'll discuss what you do in that case. And I think those ones are really cool. For the rest of the lectures, my plan is to do a bunch of examples. And then I can show you specifically how these different structures come up in particular examples. And we're going to do a bit of field theory, because there's particular subtleties that when you're doing field theory you have to take into account. And because I want to be able to do Maxwell, I want to be able to do electromagnetism. And then the question is, well, I want to go to quantization, but the question is going to be, I don't think I'm going to have time to do Yang-Mills and GR, so we might have to pick, like the last lecture, do you want to do non-abelian field theory, or do you want to do GR, which is also non-abelian field theory,
But GR you're going to do classically, I presume, and Yang-Mills
Oh, yeah.
quantum.
I'm not going to do quantum Yang-Mills because then I need BRST, but we might be able to do one or the other, or we might be able to have an extra lecture where we do
Do the long line close to the end.
Yeah. But anyway, so we'll let you think about that and decide what you want later. Thanks, guys.
Can I ask you two
Let's
questions? Well, you can turn it up. Sean, is there going to be a lecture on the week of the conference?
hold on.